Hi, my name is Ben Schmidt. I am the Lord Commander of Security Research at NARF Industries, and this is Paul Makowski.
Hi, my name is Paul Makowski. Somehow Ben slipped into the presentation that I am the assistant to the presenter. My title at NARF Industries is Director of World Domination. So hopefully I'm not too much of an assistant, and I can actually contribute.
Today we're going to be talking about embedded security in Japanese home routers. We did some surveys of various devices and found some, we think, interesting vulnerabilities along the way.
So the reason why it's kind of funny that I missed this insertion on the slide about how I'm the assistant is we've gone through 4 revisions of these slides. We've been asked to omit some details of some vulnerabilities that are still being coordinated with the affected vendors. So I missed the fact that he added in the assistant line 4 times to these slides. So it still came out in the end.
Worked perfectly.
But going hand in hand with that, you'll see a lot of black bars in this presentation, which we hope are entertaining, but not as informative as we would have hoped.
We hope eventually to fully release the details that were on the slide, but for now, we can't. So in this talk, we're going to cover sort of the motivation behind why we started doing this, mostly just because we were interested and it seemed fun. But we also wanted to explore how fast you could go from absolutely no knowledge about the embedded devices in a given country to having remote code execution as root on many of these devices. We wanted to do this simply as an exercise that sort of demonstrates the state of embedded security today. So we're going to cover sort of the landscape as it is today, specifically in Japan. We're going to analyze some of the attack surfaces that we discovered, some of the many vulnerabilities that we found during our research, and give some demos of how these exploits work, how easy they are to use, and how powerful they are, the access that you're able to gain. And then we're going to talk about all the remediation steps that we hope affected vendors and really any embedded device manufacturers should be using and should start using as soon as possible. So why did we decide to look at and hack Japanese routers? Well, for one, we did some looking around and we couldn't find very much public research on the topic. We were only able to find a single blog that even took these devices apart and posted pictures of it online. This is sort of odd for someone from the United States because we see pretty much any router that gets shipped there that you could purchase in a store. Someone somewhere tore it down, or the FCC released tear-down pictures that you can then inspect and look at. But we couldn't find very much information at all in our searching. And also, we're kind of lovers of junk hacking. We take things apart because they're interesting. Some people don't, Dave Vitale, but I think it's actually a very useful exercise. And in this case, it actually has very severe consequences. These routers matter a lot. Many of them listen on the WAN. They're very slow to update. There are a lot of vendors involved with updating them. They have to go through sometimes 5, 6, 7 different vendors before patches actually get implemented and then shipped back through all of those vendors before they actually get released to consumers. And they are notoriously insecure. Japan, mostly what we're going to focus on during this talk is our UPnP vulnerabilities that we discovered, because it is one of the most common services that is exposed on the WAN side. So China has an exceptional number of these, but Japan still has an impressive number, especially by population, that are exposed remotely to attackers. But we'll talk a little more about UPnP later. So when we started this research, we knew nothing other than we thought it might be interesting to look at some of these routers.
We've looked at other embedded devices before, but
Yes.
Nothing from Japan. So this was new territory for us, and we did this research in the US, where we didn't have ready access to Japanese infrastructure or devices. So we started out just taking a look at firmwares.
Yes. And we were in the United States during all of this, so we did not have any access to hardware to play with. All we had access to really were firmware images we were able to find and discover. And there are many barriers that make it difficult to study foreign embedded devices. One is very much the language. You need to know how to search for what you want. You need to know how to find what you want. Thankfully, we have a couple people at our company that could translate for us, but it was somewhat difficult getting started. Infrastructure varies very widely, as do the devices themselves from country to country, how they're set up, what their internals look like, how secured they are, how much research has been done on them. And obviously, acquiring hardware and things for testing was very difficult, especially in Japan, where most of the routers used by people at home are leased rather than purchased, which is not the case in many other countries. And all those things came together to make it much more difficult to study some of these devices. And we did have some difficulties with power, trying not to set my apartment on fire. We, only a little bit of smoke and melted plastic, but a power supply solved that.
Yeah. We started with just the firmwares, but as I'll explain later, when we tore apart the firmwares, we decided which devices were worth acquiring and shipping to the US. So these devices came with warning labels like you see on the slide. And yes, we kind of burnt a few. Our power specs aren't exactly the same as Japanese power specs. So we'll have to be more careful.
But thankfully, nothing too bad happened. So from our initial looks through these devices, and honestly through most of our prior work with embedded devices, there's usually very few technical obstacles to exploitation. Very rarely do you have ASLR, address-based layout randomization, which makes it much more difficult to exploit memory corruption vulnerabilities because you don't know where existing code lies. Most of them do not have dep, no execute in use, and if they do, it's not complete, so it's actually rather ineffective. Many of them do have stack or heap cookies, but it's probably just because of their tool chain. More recent versions of GCC or any other compiler they're using should be putting those in by default. Occasionally, manufacturers will disable those for speed reasons, which is a horrible decision, but very, very often, those are enabled. Sometimes safe unlinking, heap hardening, verifying the heap metadata that could be corrupted if a heap buffer is overflown. sometimes is enabled. It's often accidental and entirely based on what version of glibc or ulibc that they ended up using. And oftentimes they'll use older versions because why update? It still works.
If it's not broken, why fix it?
Yes.
The important thing to take away from this slide is any exploit mitigations that are present on these devices is typically accidental rather than intentional. The manufacturers happen to use a recent enough GCC or link against a recent enough libc, but they are not proactively going out and trying to use these mitigations like you see on workstations. So very different.
And almost across the board, everything runs as root for speed because it's much faster if you do not need to check permissions before you do things. It's so much easier when you just run everything as root. This is not good, and they should be using a lot of sandboxing, especially in network-exposed processes.
And it's also important to note that this is not just on Japanese embedded devices. This is kind of common across all embedded devices, really internationally. They're very, in a lot of respects, difficult or costly to update. And like I said, if it's not broken, why fix it? A lot of people don't feel the need to update unless they're under active attack. Unfortunately, as you hear in the news today, a lot of times people simply aren't aware that they're under attack. So we're hoping this sort of research encourages embedded device manufacturers to think more seriously about some of these low-cost mitigations.
And the landscape of embedded devices in Japan, but really all over the world, is what you would expect from the Internet of Things, a term I'm not particularly fond of, but I felt like I had to use. There are routers, obviously, but there's also anything from modems to Wi-Fi hotspots to webcams, as I'm sure many people have seen if they've looked at the news recently. And even things like internet-connected picture frames, which surprisingly some people hook directly up to the internet and let various people do whatever they want to them. There's many other examples of these devices, and they're too numerous to count. And in the future, they're only going to, that number of devices is only going to increase.
We even have a webcam in the audience back there. Somebody is telepresence. So these things are ubiquitous. They're everywhere. So here is the first of many black boxes that you will see in this presentation. So what we did is, and I mentioned this before, we grabbed as many firmwares as we could from as many devices as we could find, and different revisions of the firmware as well. And because we didn't have any Japanese devices on hand, we first set out to try to find what might be the easiest to pull apart firmwares and the easiest to analyze. And so on this slide and the next one, you see a few examples. Now these are not the firmwares that contain the vulnerabilities we'll discuss later. But these are just some firmwares that we pulled apart. And these firmwares vary widely in how difficult they are to extract and analyze. So on the easy end of the spectrum, you have a particular class of firmware from OKI. This firmware is distributed as a .bin, which is actually a .tar.gz. It's just called a .bin. And when you extract it, it's just 2 partitions. And you can mount these partitions under Linux and take a look at all of the programs and settings that are distributed with this firmware. Now, that's simple. And actually, a lot of that process is automated by tools like binwalk. If you've ever used the file command on Linux systems, the way that works is it just looks for some magic bytes in the file, and then will tell you what type of file it is. What binwalk does is you will hand it a large binary blob, and it will go byte by byte into that blob and run the same file sequence over each byte. So you may have a binary blob that you don't know what it is, but say 100 bytes in, it is a tar gzip. So binwalk knows how to extract that part of the file. Just take a look at that part and then extract that. It automates that whole process, including even mounting the file system and pulling the files out. So very simple. So that's on the easy side of the spectrum. Slightly more difficult is there was a firmware from NEC that appeared as though it was encrypted. So one recurring theme that you'll see in this presentation is we did this research for fun in our spare time. So we were going for the lowest hanging fruit, the easiest vulnerabilities. A firmware that is encrypted is not the easiest vulnerabilities to find. So we didn't look as hard there. That's not to say that there aren't vulnerabilities in those firmwares, but it just simply wasn't the path of least resistance. So in that case, there's likely some firmware that's encrypted. Now, the way that you typically get around that kind of scenario, if you don't understand the encryption, is you get a device, you open it up, and a lot of times there will be serial leads, UART leads, that you can probe. And many of these devices, the ones that we tested at least, will simply give you a root shell if you hook up to them. And if there's no serial, a lot of times there's JTAG. So very handy.
A lot less fun, but very handy.
So if you're unsure how this firmware is encrypted, you can dump a current installation and then take a look at the algorithms and reverse them. That's not something we did simply because why try harder? The next one. In one case, we took a look at a class of Buffalo firmwares that tried to use encryption. They didn't do it quite right if they were actually trying to protect the contents. They used a modified RC4 cipher with a static key, and that key is Buffalo. So all of their firmware, yes, is encrypted. Technically. But realistically, it doesn't deter us. Well, that's not true.
It did get Paul to waste a lot of his own time.
So I initially tried to reverse engineer this encryption in IDA. Thank you. I got to the point that I realized that this was RC4, and I realized what the key was, and it wasn't working when I tried to decrypt it. Turns out they just used 2 more rounds than the normal RC4, and we ended up finding OpenWRT has an encrypt-decrypt tool for these firmwares. So I spent several days trying to understand this encryption, and there's a tool out there that did it for us. That's open source.
That was my preferred way.
Yeah. So we used the tool from then on. So this is a very small sample of the different types of firmwares we pulled apart. We're going to talk about some vulnerabilities later. These examples aren't affected by those vulnerabilities. And there's going to be, we're hoping that when we have a coordinated release later, that we can release more information on other firmwares so that people can replicate the extraction process and do their own analysis.
So as far as the attack surface we found on these devices is, it's what you would expect from pretty much any normal embedded router. You've got HTTP, by far is the most common way to configure and manage these devices. In our research in Japan, most of these HTTP servers are actually not exposed on the WAN, however, which greatly reduces the attack surface of the routers. However, some FTP servers were exposed, which is a problem, but UPnP by far was the most common embedded port that was remotely exposed. And when WAN facing, this is an extremely bad problem because oftentimes, almost across the board, these servers are not well written, they're not well tested, and simply exposing it on the WAN port opens you up to attacks that involve forwarding internal ports to external interfaces, which can allow you to not only attack internal services on the routers, but also attack other hosts inside of the network, which oftentimes these hosts are not well protected. They're not patched because people were relying on NAT to protect them from remote attackers. And they no longer have that barrier between them and the internet, which makes it a huge problem. So you have file shares that suddenly become exposed. You suddenly can exploit unpatched vulnerabilities, and you can access internal web servers. You can do lots and lots of really bad things simply because that's exposed without actually exploiting the daemon in any real way. So we're definitely not the first people to look at UPnP. Rapid7 did an awesome report on UPnP security a couple years ago, and their findings were definitely quite severe. They focused on the most widely used SDKs for UPnP, Intel, Mini UPnP, and a couple other unknown SDKs that basically are Broadcom SDKs. And these, each one that they looked at, people found vulnerabilities in, and there's probably more still existing in that code base. It's been looked at more than it had been previously, but it's still very dangerous to expose that on the WAN port. However, we decided that not enough people had looked at the other category. It's a very large chunk, the fourth largest, and oftentimes these vulnerabilities are, these servers have vulnerabilities in them because no one has ever looked at them to analyze their security. No one has ever even tried to figure out who wrote the software. Oftentimes it's not maintained anymore. And all of these things are still exposed on the internet. So to get an idea of just how exposed Japan in particular is to these services, we used Shodan. If you haven't heard of it before, it's basically a search engine for vulnerable devices. You can search on common ports that embedded devices use and find per country where these services are listening. So in the case of our black box UPnP daemon, we found over 3 million hosts in Japan searching for UPnP running this daemon, and almost none anywhere else. Colombia, for some reason, has 63,000 reported ones. No idea why. We found this to be very interesting because it meant that there was a native UPnP daemon that is used in Japan and nowhere else, which means that it probably hasn't been looked at a lot. A lot of countries show this very unique fingerprint when it comes to the home routers used in their countries, because oftentimes ISPs source from native manufacturers because it's easier with the language barriers, and it's quicker to get whatever devices they need into the country. So oftentimes what this means is countries' ISP infrastructure is very unique to their country, and it means that it exposes very unique vulnerabilities that may be overlooked by people looking at global patterns. However, it's very important for countries to look at these devices that are running on their infrastructure and their infrastructure only, because if someone wants to attack your country for some reason, then they're very definitely going to be looking for these sorts of problems. Our own research, just because Shodan can sometimes overestimate the number of hosts because IP addresses may be dynamic and change, our own research indicated that there were significantly less of these devices than what Shodan reports, between 200,000 and 300,000 hosts. However, this is still a very, very large number, and there's any number of things that you can do with a botnet that is very easy to build of that size, and we'll talk about some of those.
So as you probably notice, another one of the things we had to black box is the means to identify this particular daemon. So we will refer to this as the black box UPnP daemon. Hopefully, in the coming months, we can release full details. But this UPnP daemon is really computer science security 101. It is the type of program that you would hand to undergraduate students who are learning about buffer overflows, who are learning about format string attacks, or even looking for logic bugs. Pretty much every type of vulnerability is represented in this daemon. And we just had fun trying to find as many as we could. It turned out to be shockingly easy. Now, this wouldn't be so big of a deal if this daemon wasn't running on somewhere, by our research, somewhere between 200 and 300,000 hosts in Japan and listening on the internet. So with that number of hosts in Japan, you could cause a lot of damage to Japanese infrastructure, and we'll talk about what exactly you could do with that number of hosts in a few minutes. But this daemon has everything. It's got buffer overflows on the stack. If you're more into exploiting buffer overflows on the heap, it's got that for you too. It's got logic bugs, and a bunch of other problems elsewhere in other daemons on the same device. So this is a fun slide. Initially, this slide actually showed some code.
Can you guys spot the vulnerability?
It's more difficult now to spot the vulnerabilities. So this is in this UPnP daemon. Now, you don't really need to know a whole lot else behind those black bars. You see you've got an attacker-controlled string going into a sprintf. Now, this one in particular is not vulnerable to a format string bug because it's going into a %f, or sorry, %s. But you'll notice it's a sprintf, not an SN printf, or anything that checks bounds. So that's the format string equivalent of a stir copy. It's just going to keep copying until it hits a null byte.
Checking length slows you down.
Yes. Yeah, when you're developing an embedded device, a lot of times there's pressure to be as cost-effective as possible, and a lot of times security checks slow you down. In the financial sector, it's actually intentional in a lot of respects to ignore security checks. Also, GPUs in desktops and whatnot, their drivers intentionally omit security checks. In this case, I don't think it was intentionally omitted. This daemon listens to internet traffic, so if it was intentional, it should not have been. Hit the next.
Did you talk about system yet, though?
Not yet.
That's the most fun.
Not yet. All right, so behind this black bar right there, there's a buffer, and that buffer is on the stack. So this sprintf is going to copy an attacker-controlled length onto a stack buffer, and we all know what kind of fun you can have with that. So that's one of the vulnerabilities. I'm kind of telling you the answers here because we blacked out all of the actual code. You hit it again.
Yeah.
Yeah. So there's so the attacker controls two different sprintfs, overflows two different buffers. So that's fun, and you can use these vulnerabilities to gain code execution. But what you don't see it's covered in black is this particular function has stack cookies. So you'd have to have some kind of evasion for the stack cookies. And that's hard. And we weren't trying really hard. We wanted to get the easy win. So why try harder? Oh, it's already up. Great. So why try harder? The string that's being sprintf'd into is passed directly to system. So this daemon will take traffic from the internet. This daemon's running as root, and will pass it directly into system. And it will execute any command that you give it.
And we found this function initially. The first thing we did was search for calls to system. And the first one we looked at was this function.
Yeah. So hit it again.
So,
and also there. So you've got two buffer overflows, two command injections, and hit it one more time, in 4 lines of code. Yeah, why try harder? This is the easiest. These are the easiest bugs to exploit, and this is how we initially gained code execution on this particular vulnerable device. And we used that code execution to find more vulnerabilities. So the vulnerabilities don't stop here, including there's more vulnerabilities in the UPnP daemon itself, but we already won on the UPnP daemon. Why try to find more? So we started looking at the other daemons that were listening, and that includes an HTTP daemon. All right, so before we get to the HTTP bugs, we want to show you a little demo of, and this is going to be, because we're omitting the details of the vulnerability and how to trigger it, this is going to be a very plain, very boring video.
You have to trust us. We are actually running an exploit.
Okay, so what we're doing here, if you can see, okay, so we have an exploit called shell.py. We had acquired this Japanese device, and it is on our local network. We're not doing this over the internet. And we run our exploit against it. And we get a root shell. So that took just a few seconds. And what we were exploiting there is the vulnerabilities that we just discussed, where we have command injection. So we run a few commands to demonstrate that we are in fact root on this device. And that's it for that demo. If I did show you the exploit code, it would be really boring as well, because it is so simple.
It's how many lines?
The exploit is also probably about 4 lines of code. All right, so the fun doesn't stop there, though. There's other daemons running on this device. Why don't we take a look at them? So now that we have a root shell on this device, we can try probing other daemons and dynamically executing them. The vendor who built this device was kind enough to include GDB server on the device. So we could even set up remote GDB debugging connections to these daemons. So that's very helpful. Now this device had an HTTP server as well. This HTTP server was not listening on the internet by default. But that doesn't matter so much. So like Ben had said before, the fact that this device is listening to the internet for UPnP means that this device can potentially be reconfigured to forward ports to the internal network, including its own ports. So you have this HTTP server running that's supposed to only be listening on the LAN, but you have a UPnP server that's listening to commands from the internet. You can instruct the UPnP server to forward the LAN port to the internet. So this HTTP server by default is not listening to the internet, but you can cause it to listen to the internet. So we found several vulnerabilities in this daemon as well. This daemon is another indigenous, very unique to Japan daemon, and it was clearly written. It was purpose-built for these embedded devices. It's not Apache. It's not Nginx. It's not IAS or anything famous. It was actually pretty difficult, and we spent some time trying to figure out who the vendor was that wrote this daemon and the UPnP daemon, because we wanted to tell them about these vulnerabilities. And they didn't put their name anywhere in the binaries. So it was very difficult to track them down. So this bug, it's an interesting bug. So in this case, they seemingly actually tried for security, but they made a mistake. So the HTTP daemon, if you issue a get command to the HTTP daemon, it will copy the path that you requested into a heap buffer. The problem is that heap buffer is sized according to the content length header that you pass to the device as part of the request. So there's a sanity check that checks to see whether or not the buffer is sufficiently sized to hold the path that's going to be copied into it. The problem is, after that sanity check, the size is promoted from a signed integer to an unsigned integer, and that length, the unsigned length, is copied into the buffer. And it causes massive overflow and just destroys the process space.
The part of the reason we decided to show this one is because exploitability is difficult in this case. However, the proof of concept is so short that it gives you an idea of how many vulnerabilities are present in this daemon.
It should be noted, all of these vulnerabilities, they've been reported. We've coordinated disclosure with the affected parties. Part of that is all of the black bars you see today. We're omitting details about how you fingerprint these daemons. So we don't want people to take malicious use of this information, but we wanted to provide you with some kind of idea of the severity of the issues plaguing these devices. So like I mentioned before, there is a signedness comparison issue in the content length header. So if you specify a negative content length, it's going to improperly allocate a heap buffer, and then it's going to copy way too much data than it should. So this is slightly longer than our other proof of concept. This is 5 lines. Our previous exploit was 4. So we're getting into really complex territory here. So we have a demo of this one as well.
Won't jump ahead then.
Oh, are we jumping ahead?
No, we can do a demo.
So this one is slightly more interesting. We had previously shown you getting a root shell via the Upnp vulnerability. Now we're going to use that same vulnerability to get that root shell, and then we're going to do more things with it. Okay, so in the top left, we have that root shell again, and that was the Upnp vulnerability. Now in the bottom left, we are setting up GDB on our testing laptop. Switching back to the top left, we do a process listing and determine what the process ID is of the HTTP server. Okay. So what we have in the top left is we had attached GDB server to the affected binary. And then in the bottom left, we are doing a remote debugging session with the device.
And as you can probably tell from previous slides, this particular device is an ARM device. So we're using a version of GDB compiled with ARM support.
All right, so we have control over the execution of this daemon, and now we open a last terminal, and we send the contents of what was on the previous slide, which is in heap overflow.py. And as you can see in the bottom left slide, we cause a seg fault in the daemon. We didn't actually we didn't actually take this to full code execution because we already had full code execution. So again, why try harder? Okay. So this HTTP daemon, I mentioned there was some logic vulnerabilities as well. This is just your standard vanilla path traversal vulnerability. This is another computer science security 101 problem. If you specify a path that you're going to request that is outside of the HTTP route, the HTTP daemon should not serve you that path. This daemon does. And the proof of concept for this vulnerability is our shortest one yet. It is 2 lines. So what we have here is you just import Python requests, and then what we're requesting is outside of the HTTP route. We use the .. to get outside of it. And then we're requesting this XML file, and that XML file contains passwords. So if you're on the local network, or if you're a remote attacker, but if you're on the local network, you could make this request to your friends or your enemy's router and get their admin password for the router. So that's not good. And we have a demo for this as well. And this is our last demo. So we don't actually request the file I just showed you. Again, this is us getting an interactive root shell. And now, in this case, we echo foo into /temp/bar, just as a demo. And then in our other terminal, we issue what I just showed on the last slide, and we get the contents of /temp/bar.
This becomes even more fun when you start dumping things like dev kmem.
Which is directly dumping kernel memory, which is fun.
So why does this matter? Well, you can do a lot of things with 200 to 300,000 hosts, and even more so when they're home routers that are protecting a large number of other devices on the network. First of all, you can very clearly violate the privacy of thousands of people and capture all the traffic entering and leaving that network. This also allows you to impersonate the people who are using these devices. You can man in the middle their connections, exploit end hosts on their network so that you can build an even larger botnet. You could use this as a way to hide the true source of other attacks by routing them through these devices and make it appear that innocent homeowners and people with these devices are initiating attacks, that they're coming from Japan when they could be coming from anywhere in the world. And possibly worst of all, it could very well cripple national infrastructure because of the sheer amount of data that you're able to send from these devices. Japan is very lucky to have many high-speed connections to the internet. However, this creates problems when many hosts on those networks are compromised because very quickly you can gather a large amount of bandwidth that could take out even very, very large websites or important sites across the world. Just a few more Japanese statistics that we gathered. As we've said many times, 200,000 to 300,000 of these are running the vulnerable UPnP service on the WAN. Upwards of 500,000 are running just any UPnP server, which, as we've said many times, is very dangerous to do. We did notice the most common service that was exposed is HTTP. However, the vast majority of these servers are normal web servers for your favorite websites. Very few of them are actually modems or routers that expose these services remotely. So, so where do you go from here?
Yeah, so as discussed before, the UPnP daemon in particular has every type of vulnerability in the book. We would recommend to people building these devices that you know, there are open source, ready to use stacks out there, programs out there for doing UPnP, and they are much better studied. And like we said before, the vulnerabilities that we found and we've talked about here, literally we threw into IDA Pro and controlled F for system. So it's not a game you're going to win trying to patch these vulnerabilities. Frankly, some of these daemons, you just need to start over. Another thing you can do to shore up the defenses is employ modern exploit mitigations. There's been a lot of development in this realm in the workstation space, desktops, laptops. You know, when you're browsing the internet and you're using, for example, Chrome, web pages are rendered in a deprivileged process. They are sandboxed. These concepts do not appear in the embedded world, but there's no reason why they couldn't. So make it more difficult to exploit in the first place, and in user space that amounts to no execute. Keep using those stack and heap cookies. Employ full ASLR. One problem that a lot of people run into is they think they've enabled ASLR. Enabling it on Linux in the kernel is actually insufficient. You also have to compile the binaries that you want to randomize as PIE, as position-independent executables. If you don't do that, the .text segment of the program is not randomized, and less than full ASLR is about as useful as no ASLR. And then in the kernel space, we were actually having a discussion about this last night. There's a series of patches, if you're using Linux, that we recommend, we run, frankly, that add a lot of these mitigations to stock mainline Linux. And there's a lot to be said on that, and if you're curious, I'll talk to you after.
For hours.
For hours. But another thing to do is fail closed. These UPnP daemons are listening on the internet. We kind of doubt that that's actually necessary. It's not, they had separate update mechanisms. The UPnP daemon is not their update mechanism. Frankly, the update mechanism should probably be the only thing, if anything at all. The update mechanism should be the only thing listening on the internet. And if you do have update systems, if you have the need to do remote administration, ISPs sometimes require this, then do so with key-based authentication, and there's proven options out there for this. Like we said before, there's no reason to run everything as root. Even with those command injection vulnerabilities, if that UPnP daemon was running as the user nobody, we probably wouldn't be able to do a whole lot, but it's running as root. As much as possible, sandbox things. Chrome does this. It's spreading to a lot of other programs. Adobe Reader does this, actually uses Chromium's sandbox to a certain extent. On Linux, this is implemented with seccomp BPF. On Windows, they don't actually have a proper sandboxing. Some people might argue with me on that. They have integrity levels, which is close. And then on OS X, there's seatbelt profiles. And then finally, if there is an open source tool that you can use, FTP, HTTP, UPnP, daemon, use that. Often they are more audited. And more importantly, as the vendor, if you get burned because there's a vulnerability in shared code, it doesn't look as bad because everyone runs that code. Okay, I guess I had a few more suggestions.
He always does.
Yeah. Encrypt and sign firmware. That would make it more difficult for us to do this analysis. Deter physical access. Don't allow us to get root shells by just plugging into UARTs. Don't give us JTAG. And whenever possible, don't write things in memory unsafe languages. Write it in Python, or in Japan, Ruby is very popular. Write it in Ruby. There are fewer classes of vulnerabilities that you might expose. Yeah. So what doesn't work is trying to make it difficult to extract firmwares. That will just delay people. And hacking infrastructure is very much in vogue now. It's very popular. As endpoints, as workstations have become more hardened, it's important to also take a look at what sits between you and the internet. Oh, wow. How many more do we have?
Enough. Firewall everything off. Protect everything in your internal network, because NAT is not really sufficient. I know it's probably not a buzzword anymore, but defense in depth, protect everything on your inside network, because things can and will fail, especially things like embedded devices. Whenever possible, run your own firmware. Things like OpenWRT, DDWRT are very much more hardened, have been analyzed a lot more, and are generally safer. Let someone else be the lowest hanging fruit.
So in conclusion, we're hoping that there's more interest and we can maybe help answer some questions about researching Japanese modems and routers. We hope to release more data in the coming months on how to pull apart these firmwares. Although neither of us speak more than a few phrases in Japanese, we were still able to understand how to attack these devices. The cultural barriers are not high enough. And finally, the fixes aren't simple, but we listed a few different things that can help. We'd like to thank Google Translate, Yahoo Auctions, and take any questions if anyone has any.
Have the vendors committed to providing fixes?
So the question is, how have the vendors committed to providing the fixes? So some of these, it depends on the vulnerability, frankly. So the UPnP vulnerabilities, we let them know about months ago. The HTTP vulnerabilities, which is why we were more cagey, we revealed less information about. Those are more recent. So we're hoping to stick to this 3-month-ish time frame. we're understanding that the process in Japan is different than the process in the US.
And patching embedded devices in general is very slow to begin with. You definitely are risking by remotely patching things your entire internet infrastructure going down, and that's scary for very good reasons.
Yeah, we have at narfindustries.com/codeblue2014. We hope to add more information in the coming months on those items.
Are you interested in doing research for any other country outside of Japan? Which one will be next?
So I don't want to speak for Paul, but I've been looking.
Repeat the question in
Oh,
English.
the question is, outside of Japan, what other countries are we looking at researching next? I personally, during some of my research, find a lot of the devices in China very interesting. They have a wide variety of services, and it's actually very disjointed, so I think there's a lot of interesting things there. But I also would like to look at some Russian devices, which is similar, but there are less remotely exposed services. So I think it would be interesting to look at those too.
The reason why we looked at Japanese devices is our company has an office in Tokyo, and we were curious what kind of code was running between us and the internet. Unfortunately, our expectations proved true in that we didn't think the code was very secure. But we want to reiterate that if we had an office in another country, we would expect the exact same outcome. This is an international problem, not just a Japanese one, but we're hoping that there's more interest in the Japanese sector now. Thank you.
すみません、それではもう一点だけ逆に
One additional question. Which country do you think has the best practice or good practice in terms of home router? Which countries are more secure than others?
So
The question is, which country do we think has the best security track record for embedded devices? And in my opinion, that's the best of the worst.
Everyone still has these problems.
It's all bad.
Countries where more reverse engineering of these devices and research has been performed, generally the devices are somewhat harder to attack. But by and large, so the United States, for instance, has had people present at many, many Black Hats and DEF CONs vulnerabilities in Verizon routers and Comcast routers, all the major ISPs, really. And we still have these vulnerabilities.
Yeah.
They're sometimes harder to exploit, but not all the time. So really, no one is the most secure right now.
It helps though, I think, to have a healthy security research community attacking your own infrastructure. And that's common in the US, it's common in the European Union. And perhaps we were just Googling poorly, but it didn't seem as common in Japan. But at the end of the day, everyone keeps making the same mistakes in embedded devices. And so our suggestions for fixing the problem are not to try to patch all the vulnerabilities. It's to make them more costly to exploit.
ありがとうございます。
Thank you very much.